Good morning, everyone. Thank you for joining me this morning. My name is Patrick Fisher. I'm the product manager for SafeGuard Profiler and SafeGuard Sentinel at ACM Facility Safety. Also going to be joining us on the line in just a minute or two here is Brad Castle in Software Business Development with ACM. You can email me your questions, pfisher@acm.ca. So we're here today to talk about SafeGuard Profiler, and Profiler is a tool from ACM that's used in the analysis of process safety during conceptual and detailed design. Importantly, here for this presentation, there's three separate packages of SafeGuard Profiler. There's a LOPA package, which is for your Silv determination facilitators, anyone doing LOPAs, risk graphs, or safety layer matrix. Includes bow tie visualization, Hazop import, etc. That's what we're going to be talking about first. There's also a package for the safety engineers, the Silv package. That's going to do all of your SIF design, your safety requirement specification, some failure mode and optimization, and includes the failure rate database. As well, we have an expert package, which combines the functionality of the two and adds in even more to create an integrated database between both your Silv determination and Silv verification, validation, and SRS. So just generally, SafeGuard Profiler uses risk visualization to help your analysis and design go faster. So we reduce your engineering time and costs, optimize the number and reliability of safeguards for better operation, and reduce your capital costs and maintenance costs. Also help you guide operations in safe operation in the last section of the safety life cycle, which is when the plant is actually running. These visualizations help instantly show the safeguards, whether they're meeting the required SIL levels and tolerable frequencies, and reduce your overall SIL determination and SIL verification validation time by up to 50%. Starting out with a LOPA package, we're going to be talking about for the first part of this presentation. I'm going to set the stage and talk about a crude distillation unit, so we're all talking the same language. I'm going to walk through a very high-level and brief Hazop to give you an idea of exactly what we're doing at the LOPA stage and how we got the information. I'm also going to introduce and walk you through a LOPA and talk about risk visualization, in particular the bow tie. And throughout all this, you're going to see how SafeGuard Profiler does this better than what you're currently using. So I'm starting out with a crude distillation unit, as I mentioned there. This is the core of every refinery. It's what turns the crude oil into the products that we can sell for a lot more money. Even if you're not working in the oil and gas industry or you're not familiar with the crude unit, you'll be able to see that there's similarities to whatever you do. It doesn't have a whole lot of unique equipment, so you should be able to follow along, no problem here. Give you a bit more of an engineering view here. If we go into a very simplified engineering drawing of that same crude unit, at the bottom left, we have feed coming in from a pipeline or another unit, and that's going to be pumped through a heater to bring it up to temperature to actually go into the column. Some of it's going to go up the column. Other parts are going to be at the bottom and go through a reboiler, get them even hotter. Some of that is going to be drawn off as vacuum products. The rest of it's going to be sent back into the column. Going up the column, there's going to be a number of pump arounds, anywhere from a couple to a dozen pump arounds, and they're just drawing off some of the column, the material, cooling it off, and either sending it back down the column or drawing it off as products. These are the products you'd recognize. Kerosene, gasoline, jet fuel are going to be coming out of these pump rounds. Finally, we have the overheads at the top, which are cooled off. Some of them are pumped back in, but the overheads are going to be your really light ends like propane and butane. So we spent hundreds of millions, if not billions of dollars building this crude unit. And what we want to do at the design stage is figure out what can go wrong. So how bad could it be with your crude unit? Well, you could blow it up. You could have a fire or explosion within the unit. It happens relatively often in the world. Every couple of years, there's something in the news where there's been a major refinery fire or explosion, and it can often be in this unit. So you want to do at the Hazop stage is identify how can that happen. And one way is overpressure, or getting high pressure within the unit. So we identify that as a deviation in the Hazop. The next step is to look at the engineering drawings and say, what can actually cause this overpressure? So the Hazop team that did this identified some really high-level causes. One of them would be losing your pump around flow. Another one would be losing your overhead draw, losing your vacuum draw, losing temperature control in any of your pump arounds, or even a line break in the reboiler. Any of these can cause overpressure. There's actually a lot of ways to overpressure a crude unit. Going forward here in this Hazop, because we want to keep it simple, I'm just going to be looking at losing your pump around flow. Once you lose your pump around flow, we need to determine what the consequences of that are. We already identified the overpressure, but after that, there's leaks or rupture, loss of containment, fire and explosion, and ultimately there's going to be multiple consequences coming from that, such as your hazardous personnel, damage to the environment, economic impacts, and reputation impact. These will depend on your company, what categories they have, but generally they'll all fit into these 4 categories. Going forward in our Hazop here, again, to simplify it, I'm just going to look at hazardous to personnel. The next thing we need to do is risk rank. So we start with a risk matrix, and this should be familiar to you if you do any sort of risk analysis. Your company would have a standard risk matrix to use. It may not look exactly like this, but it's similar. The way it works is you look at your likelihood of the initiating event here, which is losing your pump around flow. And that's going to be a number like 1 in 10 per year. And then we look at the severity of the consequence. So we're going to look at consequence of overpressure. We identify it as mass fatalities. It's pretty realistic in an overpressure scenario in a crude unit. Where these 2 lines intersect is going to be your risk ranking, and we have an extreme risk at this point. Again, not unreasonable. These are very severe instances we're looking at. So the next thing we need to do is figure out how to lower that risk, and to do that we're going to identify our safeguards. Remember, the only cause we're looking at right now is losing your pump around flow. So what's a good safeguard? Well, one of them is going to be your low flow alarm on a pump around. It's going to pick it up, you can shut down the column. Also, always good for pressure, your PSV or pressure relief valves that are going to go to flare. These are pretty big on a crude unit. As well, the designers of this system knew that you would need a safety instrumented pressure trip, so they put that in, and that's going to detect your high pressure and trip the heater. We'll talk a lot more about that in the second half of this presentation. Once that information is done, we're going to put it into a spreadsheet. It's going to look kind of like this. We've got our causes, our consequences, and risk ranking along with safeguards. Remember, though, that this was only for a single cause and a single consequence of that cause. That's all we'd identified at that point. So we need to repeat this for each of the consequences first. We identified 4 other consequences just for this one cause, all with a high risk ranking. And then we need to go further and do all of the causes of overpressure. So we had 5 causes, each with 4 consequences, making 20 consequences overall. As you can imagine, this information gets quite large quite quickly, almost exponentially. And even just looking at this is only 1 deviation of 1 unit in an entire facility. Anyone who's dealt with Hazops knows that there's a lot of good information in them, but you end up, the amount of information you have to sift through in order to get the good information is almost unbearable to deal with. And a Hazop doesn't go all the way to answering some of the questions we would expect to see from a risk study. For example, we started out with this high risk ranking, this extreme risk, and we've added safeguards which are going to change the likelihood of overpressuring by a certain amount, but a Hazop doesn't tell you how much you're going to change the risk ranking. So you can't really answer, are we safe yet? Another thing here is we have a total of 7 safeguards identified through our 5 causes and 20 consequences. Is that enough? We don't really know. And do we have too many? You can't answer that in a Hazop. That's how over-instrumented systems happen. Is if you just do a Hazop, you're going to end up with lots of safeguards that you don't necessarily need. What about that one safeguard, the safety instrumented function that we put in at the bottom there, the pressure trip? Do we need it? There's a lot of maintenance involved with it, and testing and life cycle costs. So if we don't need it, well, that'd be good. But if we do need it, what reliability does it need to have? We don't really have an answer for that from a Hazop. And if you are getting your Silv levels from a Hazop, you shouldn't be doing that. That's not a correct Silv determination method. The answer to these questions is a LOPA, or Layer of Protection Analysis. The Center for Chemical Process Safety defines a LOPA as a process of evaluating the effectiveness of independent protection layers and reducing the likelihood or severity of an undesirable event. What does that actually mean? Well, what it means is we are putting numbers to the Hazop in order to answer what is the actual risk? Do we have enough safeguards? Do we have too many safeguards? Do we need a safety instrument function? And if so, how reliable does that SIF need to be? So LOPA is a Silv determination method. A big difference between a LOPA and a Hazop is in a Hazop we only looked at one cause at a time. In a LOPA we're going to look at a whole bunch of causes at the same time. In this case, all 5 we identified in the Hazop are going to be analyzed at once. We're going to analyze those because they all lead towards one overpressure scenario. Overpressure of the column, fire explosion. And then in a traditional LOPA, we're going to look at only a single consequence, which is going to be your multiple fatalities in this case. Just generally, these terms are called a hazardous event and consequence. You can see lots of causes can lead to hazardous events. In this case, the hazardous event can lead to one consequence in a traditional LOPA. Next, we're going to layer in our safeguards, or independent protection layers. There's 2 different types of safeguards and IPLs. There's preventative, which are going to prevent causes leading to the hazardous event. And then there's mitigative safeguards, or mitigation safeguards, which are going to prevent the hazardous event leading to the consequence. In this case, in the Hazop, we only identified preventative safeguards, which is not surprising because the event is so severe. In smaller events, like minor loss of containment, you're going to see mitigation safeguards like fire and gas detection and operator rounds. So it's anything that prevents the hazardous event from leading to the consequence. In our case, we identified alarm safeguards, the PSV, and an SIS on our preventative side. In a LOPA, the next thing we're going to do is each cause is going to be given an initiating event frequency, or IEF. This is saying how often is it going to occur. An example IEF would be a control loop, which we would give 1 in 10 per year frequency of failure. Next thing we're going to do is we're going to get a mitigated frequency. We're going to add all those initiating event frequencies together, and that's going to give us a frequency of the consequence, a mitigated frequency. Your LOPA scenario is going to be closed if your mitigated frequency is less than or equal to a tolerable frequency. The tolerable frequency comes from your company standards and is going to be based on society's acceptance of these hazardous events. An example that's commonly used is for fatalities in a single event, 1 in 10,000 per year. So the way we modify our initiating events to create a mitigated frequency less than or equal to the tolerable frequency is by giving each independent protection layer a probability of failure on demand or risk reduction. What this is saying is that there's a certain chance that that safeguard will not work. An alarm may not be acted on or may be bypassed, and a PSV may not lift. If every safeguard worked every time, we wouldn't need multiple layers of protection like we do. In this case, we have 3 layers of protection identified on each cause. So what we do is we multiply the initiating event frequency by each of the PFDs on the line and add them all together to get our mitigated frequency. If we've done it correctly, our MF is going to be less than the TF, the tolerable frequency. I mentioned that this was a traditional LOPA. You're going to be looking at just a single consequence at a time, but is there any real reason to only look at one consequence? And the answer is no. SafeGuard Profiler allows you to look at multiple consequences of the same hazardous event at the same time. So in our case, in the Hazop, we identified 4 different consequences, all coming from the same overpressure. Those can all be analyzed at once. with lines pointing to each of them. So all these causes can lead to the hazardous event, and the hazardous event can lead to all of the consequences. If we had any mitigation safeguards, they would show in here, possibly only covering one or two of the lines, depending on what the safeguards were. Again, that's a feature of SafeGuard Profiler, which you won't find in other tools. Another visualization used within Profiler is the LOPA graph, it's called. So what this is a representation. We have the actual risk level with the MF, the tolerable risk level, which is the TF, and between them there's a certain risk gap, meaning that you haven't met your tolerable frequency with your mitigated frequency. If you want more information, you can always look down at the numbers below, and if you know what those mean, that's great. But basically what the risk gap is saying is if we had a SIF to cover this scenario, that's the reliability it would need to be, and that's automatically generated by Profiler. In this case, we need a SIL2 SIF to cover this scenario. Let's look back at a traditional LOPA. Once again, this is the spreadsheet method, as it's called. We're going to be looking at only one consequence at a time in this method. You don't get that benefit of the bow tie where you're looking at lots of consequences at the same time. Our causes are listed on the left, and our safeguards or independent protection layers are going to be listed on the right. Now this is the data straight from the Hazop loaded into LOPA, and this is what your team is going to see while you're doing this layer of protection analysis. So it's a little bit hard to distinguish what's going on. In fact, if we ask the same questions of the Hazop, we don't really have answers to them. Are we safe yet? It's not really clear from this. Do we have enough safeguards or too many safeguards? You can't tell from a spreadsheet like this, certainly not if you have too many safeguards. What about that SIF? Do we need it? And what reliability does it need to be? Now, someone trained in the use of this tool and the LOPA method can see that number right there tells you that same answer, but it's small, it's hard to tell, and the team certainly can't follow what's going on and know what is happening with that SIF. So let's instead look at a bow tie, such as would come out of SafeGuard Profiler. Once again, we've loaded in our Hazop data, and what we have here is all of our causes, all of our consequences. So we're looking at 4 consequences. So now we're doing our LOPA work 4 times as quickly compared to the spreadsheet method, and our independent protection layers. We also have our LOPA graph split across the screen here for more information. The first thing a team's going to notice in this bow tie is that there are an awful lot of alarms. We've ended up with 1 alarm on each cause, and they're all different alarms. That's not unusual coming out of a Hazop because of the way the analysis is done. What we can see in this bow tie is, boy, it would be great if we could replace all of those multiple alarms with just a single alarm that would be as effective, and often you can. What happens is your mitigated frequency will not be affected by changing multiple alarms into a single alarm generally, or they will be changed. It'll be changed in a very minor amount. So if you look at the LOPA graph, in this case, our risk is not changing as I'm going between multiple alarms and a single alarm. So what we get right there is a benefit of having fewer safeguards, which means less operational difficulties, fewer or less capital costs, and less time spent doing maintenance. Next question there is, are we safe yet? And the answer is no. Our mitigated frequency has not met our tolerable frequency, and we're still seeing a risk gap within that LOPA graph. And that SIF, that kind of leads to the next question: do we need that SIF? And the answer is obviously yes, because we still have color in our LOPA graph. We could add in a whole bunch of safeguards to cover a SIL2 gap, but that's pretty hard to do. And that's represented by the yellow. If it was a little lower, it would be blue, showing that you could cover it theoretically. So the next question is, what reliability does that safety instrument function need to have? And the answer, again, is quite clear because it's right there in the LOPA graph. We need a SIL2. If you look at the numbers here, even more specifically, we need a risk reduction of 131. So what we're going to do in the LOPA is we're going to take that Silv2 and actually apply it to the safety instrumented function, increase the reliability, and complete our LOPA scenario. Our LOPA graph is now, it's got no color in it. The mitigated frequency has exactly met the tolerable frequency, and our bow tie is nice, simple, and clean. It means our LOPA analysis is done and we've gotten all the benefit we can out of it. Both we are safe and we have as few safeguards as possible in order to reduce those capital costs. The next thing you should do, or you could do, is go a little bit further with your LOPA. Contingency planning. We have this single alarm safeguard, and obviously it's pretty important at this point because it's covering a lot of causes going towards overpressure. So what we're going to do is we're going to look at what would happen if we didn't have that safeguard. And SafeGuard Profiler will automatically calculate this for every safeguard that you have. It'll calculate without that what is going to be the risk. And we can see the LOPA graph updated to say there's going to be a Sil1 gap. We will have a risk gap. It'll be somewhat small. So next thing we need to do is say, how are we going to deal with that gap within operations? Since this can be done in the LOPA session, you're going to be asking the team, the experienced operators, what can we do? And they'll tell you things like, you know, we can continue to run as long as someone's watching the pressure on the column and ready to shut it down. So we can do that, and that's the contingency. A contingency won't typically have the same risk reduction or PFD as the safeguard it's replacing. In this case, it's only about half as reliable. So what we're going to do is look at the amount of risk that's left. It's green. It's a relatively low amount of risk, and management can decide ahead of time what levels of risk are acceptable to run at for how long. So basically, we can't run forever at this risk because our mitigated frequency is higher than our tolerable frequency. We can run for a short period of time. In this case, management has said 24 hours. So we're going to put that right in to our contingency plan, repair or reinstate the high pressure alarm within 24 hours. What you get is a document at the end that lists every single safeguard in your facility, along with what is the risk without it, and what can we do to bring the risk to an acceptable level, and how long can we run at that rate. So your operations knows what they need to do to keep the plant running in a safe state at all times. And this is a feature unique to SafeGuard Profiler completely. At that point, you've completed your LOPA and contingency plan analysis. So what has SafeGuard Profiler done for you so far? We took this Hazop data. There were a total of 20 consequences. And we put it into a single bow tie. So this is all the same data from this sheet is over here. In fact, you could fit about 24 pages of Hazop information onto a single bow tie. So there's pretty considerable visual compression, as it's called. Next thing, SafeGuard Profiler helped you actually analyze your scenario, both in reducing the number of alarms and making your mitigated frequency match your tolerable frequency. It told you what that SIF reliability needed to be. Comparing that to a spreadsheet, you can analyze 4 times quicker or even more, depending on how many consequences you have, because you can analyze more than one consequence at a time in a method that's simpler for the team to understand and gets you better results in the end. SafeGuard Profiler also helps you with contingency planning, so you get that document at the end that your operators can use to operate your facility safely, along with telling you all the back end, what is my risk, and how long can I run with that risk. Finally, and possibly most importantly, at the end of the Hazop, we had 7 safeguards overall from the 20 consequences. The bow tie helped us remove 5 of those and add and replace them with 1. So we've gone from 7 safeguards to a total of 3. Even if you could remove just one of those transmitters and alarms, because you no longer need it, possibly, you will have saved thousands of dollars. and that's only for one scenario of one unit in the facility. So multiply that by the number of scenarios you're looking at, and you could be saving millions to tens of millions of dollars in capital costs along with testing and maintenance costs. So overall, that's SafeGuard Profiler and the LOPA package. I'm now going into the questions here. If you have any questions, put them into the chat or email me them at pfisher@acm.ca. I do have a couple questions to go over. The first one here, how do we transfer Hazop data to SafeGuard Profiler from Excel worksheet or any Hazop software like PHA Pro? And SafeGuard Profiler has a technique to do that. It's very simple mapping. I will actually show you that in the tool at the end instead of showing you it right now, but absolutely you will get to see that. And the next question is, can Profiler identify common cause failures? In terms of a LOPA, that is going to be up to the team and the facilitator. Unfortunately, there's no real way to automatically identify common cause failures. The people in the room in your LOPA session are the ones who best know what common causes are. There's no way to tell that automatically. Another question is, how does Profiler help reduce the number of safeguards? And that was in the bow tie. We replaced 5 alarms with a single alarm, reducing your overall number of safeguards from 7 to 3. So we reduced a pretty considerable number of safeguards through the bow tie method. And that is unique to Profiler in that it links the LOPA, the power of a spreadsheet LOPA, with the visualization of the bow tie as you're doing that. Now we're going to go on to the Silv package. And for those of you just joining us, I know there were a few people who joined us in the middle of that last section. My name is Patrick Fisher. I'm the product manager for SafeGuard Profiler and SafeGuard Sentinel at ACM Facility Safety. Also on the line here, we have Brad Castle, who's in software business development. Because of the number of people we have on the line, we're going to be answering the questions at dedicated periods. So just enter them in the chat within the WebEx session. If you feel it's too long to ask within the chat, you can either email me at pfisher@acm.ca. So again, for those of you who just joined us, SafeGuard Profiler comes in 3 different packages. The first one is the LOPA package, which is for your SIL determination facilitators. That's going to include your LOPA, your risk graph, and your safety layer matrix, along with that bow tie risk visualization, the Hazop import, and contingency planning. That's what we just talked about. There's also a Silv package, which does your verification validation. Comes up with your SIF functional requirements, optimizes your SIFs, comes with a built-in database, and helps you generate your safety requirement specification, or SRS. That's what we're going to be talking about in this next section. As well, there's an expert package which combines the two and gives you an integrated database between your SIL determination data and your SIL verification validation data. So what we're going to do in this section, I'm going to set the stage and talk about the crewed unit again. It's a little overview, background on the Hazop and LOPA that we just did, so that to catch people up. Then we're going to walk you through designing a safety instrumented function. So what is PFD and reliability? How do you calculate it? How does voting impact PFD? And how do we optimize our test intervals? We're also going to determine the potential failures of a SIF and what to do about them, and build a safety requirement specification. Throughout this, you're going to see how SafeGuard Profiler does this better compared to spreadsheets or competing tools. We started that entire analysis around a crewed unit, and in particular, we were looking at overpressure of the crewed unit. We identified back in our Hazop that there was an extreme risk to hazards to personnel. So once we loaded all that data into our bow tie here, with our causes we identified and consequences, and simplified our system, single alarm instead of 5, we said we would take that SIL2 gap and apply it to the safety instrumented function. When we did that, I said later on we'd come back to how exactly to do that. Well, that's the stage we're at here. So what is a safety instrument function? For that, we go to the IEC 61511 standard, which says it's a safety function with a specified safety integrity level which is necessary to achieve functional safety. What the heck does that mean? Well, on the right, we have an SIS loop. On the left, we have a BPCS, or Basic Process Control System, or PLC loop. What's the physical difference between these? Not a whole lot. I've heard people say it's voting. That's not necessarily true. The only real difference between these two is that SIFs have a defined life cycle. It's defined by the IEC 61511 standard, or ANSI 84, which are the same thing, essentially at least. The ACM split this life cycle into 4 steps. There's the concept stage, your feasibility analysis, hazard and risk assessment, and SIF requirements. That's what we just did. Then there's the next stage, which is going to be your safety requirement specification, your actual engineering of the SIF, and determining your test intervals. Next step is going to be your implementation, which is where you're going to do your factory acceptance testing. You're actually going to go to site, install it, test it before you run, and then finally the 4th section, which is going to be your operations. This is the longest section, and that's where you maintain the SIF, you proof test it, you repair it, and you manage change. ACM split this into 4 sections, and we call that the quad model. Quadrants. So there's 4 quadrants. SafeGuard Profiler is going to fit into all 3 quadrants from concept to implementation, whereas ACM also has a tool for quadrant 4 called SafeGuard Sentinel, which helps you operate your facility in a safe manner. This next part of this presentation is going to be specifically talking about the design stage. So how do we build our safety requirement specification? How do we do our engineering work? If you want more information about quadrants 3 and 4, just send me an email, or anyone who contacted you to join this session can pass you on to the right person. Back at the concept stage, we identified that we needed this safety instrumented function that's going to trip the heater. Now we're going to go into the steps of actually designing that. So I'm going to zoom in on it, and here's still our column, and there's our safety instrumented pressure trip. Simply enough, we have a sensor, we have a logic solver, and we have a final element. This is what makes up a safety instrument function. They would normally be arranged in a diagram like such, so that the actions move from left to right. Just generally, a sensor is going to detect the process deviation. A logic solver is going to act on that process deviation, determine what to do to act on that deviation. And the final element is going to act to bring the system to a safe state. This is called a reliability block diagram, which is just a visualization of what your SIF is going to look like. Overall, this safety instrument function has a certain reliability, and we're trying to determine what that reliability is and how good it could be. To do so, we first need to look at the reliability of an individual element. In this case, let's look at the sensor. So what is an element's reliability? For this, we go to a different standard, which is the IEC 61508 standard, heavily referenced by the 1511 standard. But in the standard, the reliability is going to depend on a number of factors, including failure rate per million hours, dangerous failure fraction, or safe failure fraction, they're inverses of each other, your proof test intervals, your test coverage, your mean time to restoration, so how long does it take to repair it, and diagnostic coverage for smart sensors. How does this actually all combine together in order to make a reliability? We look at an equation that looks about like this. It's pretty complicated, but it's got those factors in it. Some people use a simplification, which is shown below there, that just relies on the dangerous failure rate and the test interval. This is handy if you're doing spreadsheets or doing any calculations by hand, because obviously you're not going to want to plug in that giant equation at the top every time. However, SafeGuard Profiler does not use the approximation. uses the full equation because there's a built-in database that contains all the information you need to actually fill out this equation, and it's going to automatically calculate using the full thing. So if we go to our custom failure rate database, and we have a sensor that's similar in our facility, and we've got a failure rate, our test coverage, we say we want to test it every 60 months, and we've got a 75% diagnostic coverage. We're going to get a reliability for this sensor of around 97 out of 100. Earlier, we were talking about probability of failure on demand. That's going to be 3 out of 100. They're inverses of each other. You do one minus the other. So we're going to switch between them a couple times here so that the math is easier to follow. But just remember at all times, it's just one minus the other. Again, we look back at our full SIF, and we said our sensor successfully detects 97 times out of 100. Our logic solver, to determine that, we're not actually going to do the reliability equation. We're going to get this straight from the vendor. They're going to say successfully solves 9,999 times out of 10,000. Then our final element, we go back to that reliability equation, and it's going to successfully act 88 times out of 100. This is fairly realistic for a safety instrumented function. Your final element will typically be the least reliable, and your logic solver will generally be the most reliable system, with the sensors somewhere in between. To determine the overall reliability, what we're going to do is look for the chances of all of them working. So we multiply it together and get that the SIF is successful 854 times out of 1,000. What does that mean for PFD? Probability of failure on demand is going to be 0.146 of this current design. Let's look at that compared to what we needed out of the LOPA. We said we had a Silv gap. In fact, we said the PFD needs to be 7.63 times 10 to the negative 3, and we've got 1.46 times 10 to the negative 1. Basically, the probability of failure on demand so far is too high, and the reliability is too low. So we need to go further in our design. Next thing we're going to do is look at some voting. So for ease of calculation here, I'm going to show you voting on the sensor. We determined that the probability of failure on demand of a single sensor is 3 out of 100. What if we put a second sensor in there and voted them 1 out of 2? So if one of them detects a process deviation, we're going to shut down. Our new reliability or probability of them failing is going to be the probability of both of them failing. They both need to fail in order to not detect the process deviation. So we multiply them together, and we get probability of both failing as 0.0009, or about 100 times more reliable than a single sensor. However, now we've done 1 out of 2 voting, so that means if one of the 2 of them spuriously detects a failure, spuriously detects a process deviation, it's going to trip. So what that means, the failure rate on the sensors is twice as high, which means twice as many spurious trips. 1 out of 2 for sensors is a bad combination generally because you're going to be tripping a lot. So that brings us to a different setup, 2 out of 3. You see this pretty commonly. So if 2 of them detect a process deviation, we're going to shut down the system. The probability of 2 out of 3 of them failing is 0.00257, so about 10 times more reliable than only having a single sensor, and about 10 times less reliable than having 1 out of 2. Of course, the failure rate and spurious trip rate here will actually be lower than either 1 out of 1 or 1 out of 2. So it's 2 out of 3 is a very good voting system, but you can, that kind of begs the question there, can we choose any voting option that we want? Why are we limited? The answer is yes, you can choose any voting option. Here's your equation that you're going to use. Once again, we have a pretty complicated equation. The M is the number of sensors that are going to have to detect the deviation, and N is the number of total sensors. So you're going to have to iterate this equation a number of times. Compare that to using SafeGuard Profiler. We're going to automatically do this calculation for you and show you the impact of all voting schemes up to 29 out of 29, and any combination thereof. In fact, if you wanted to, you could get even bigger SIFs depending on your system. If you were to actually iterate through 29 out of 29, you would be looking at 4,930 iterations of that voting formula. You wouldn't want to be doing that by hand, that's for sure. And even in a spreadsheet, it gets very complicated very quickly. But it's done automatically for you in SafeGuard Profiler. What's it going to look like? Here we have our reliability, the number of positives on the left out of how many. If we go to 2 out of 3, we see our reliability is 99.744 there. But we could even do, 5 out of 5. We have a pretty low reliability, or 1 out of 5 where we have a very high reliability, but we're going to be tripping a lot. So let's look back to our reliability block diagram. In my sensors, I've put 2 out of 3 voting that we just determined. And the final elements, I jumped ahead a bit and did 1 out of 2 because we really need to bring that reliability up. And complicated voting schemes on final elements can get pretty tough. Tough to actually design and build once you get into your facility. At this point, have we actually met our reliability? You can see the numbers there, but I'm going to show you another visualization that's used by Profiler, and that's going to be your Silv graph. What this shows, the colored part, is your current SIL rating, and the target SIL rating is the gray there. So at this point, we haven't met our required SIL. We're at a SIL 1, and we need a SIL 2. Now what are we going to do? Are we going to put more voting in? Well, we could, but that would get complicated quickly, so we don't really want to do that. We can look back to the reliability equation, and we said it was calculated based on 6 values there. Failure rate, mean time to restoration, diagnostic coverage, those are going to generally come from your vendor, so it's kind of tough to change those. We can change them and then find a new vendor, but the easiest thing to change is going to be your proof test interval. And in fact, the equation is most, it pivots the most on the proof test interval. So small change in proof test interval makes a big change in your PFD. What you're going to be able to do in Profiler is choose proof test interval to pivot the entire SIL calculation on. So we started with 60 months proof test interval originally. We can then go into optimization mode and just click this current SIL rating and drag it over to our target SIL rating. And while we're doing that, Profiler will calculate your proof test interval you're required to meet that SIL rating. So to get our current to meet the target, we're going to need to up that proof test interval to 36 months. But that's just what we have to do in order to hit that target. The equation, or the pivoting that I'm talking about here, where we're changing the proof test interval, we could also do that on failure rate if we wanted to. So if we wanted to know what failure rate of a valve would it take in order to get our target SIL rating, we can also do that. Or diagnostic coverage, any of the values within the equation, as long as we're doing one at a time. So let's go back to our reliability block diagram, looking at our PFDs. Our probability of failure on demand and reliability is actually better than we require. So that means we're complete at this point. We've met our required reliability. So now we know what we need to build the SIF to. Next thing here to look at is, what about all this equipment that we put in that we're voting all over the place? What happens if one of those sensors fails or is not adequately tested? If something goes wrong with it? What just happened to our probability of failure on demand and compared to what we needed? SafeGuard Profiler automatically will calculate that for you. So what we're looking at here is a chart that lists your elements that can fail, how they're going to vote when you have a failure. So in this case, we had 2 out of 3, so now we're going to vote 2 out of 2. Then there's the probability of failure and demand that the intended design, that's our SIL 2. But if we have that failure, here's our new SIL. It's going to only be a SIL 1. That's not so good. So what can we do at that point? Well, one of the best things to do is to, again, change that test interval. So we can look at the contingencies and redo the optimization. And it's going to tell us in order to meet that reliability, we're going to have to continue to run with the test interval increased to 6 months. So this doesn't necessarily mean that you're going to run forever with 6-month test intervals. That wouldn't be feasible. What this means is you can look at this and say, when was the last time I tested it? It was 5 months ago. Okay, I'm still safe. I can continue to run, but I need to fix that because otherwise I'm going to need to keep proof testing it over and over and over again. But if it's been 2 years since I last proof tested it, I should shut down because I'm not meeting my required reliability. Finally, we're going to automatically calculate the PFD with the 6-month contingency there, and you can see it meets the original PFD. Same thing is going to happen with your valves. For those ones, you're going to have to increase your test interval a little further, but you can get back to the same reliability once again. The next section to do is the Safety Requirement Specification, or SRS. From the 61511 standard, this SRS states the requirements of the protective functions carried out by the SafeGuard. It includes both the intended design and functional requirements. Once again, what does that really mean? It's basically saying everything you need for that SIF to work. The intended design has 22 recommended fields from the 61511 standard. You could have a different number. And Profiler comes with those 22 fields already built in. So linked with your SIF is going to be a safety requirement specification. It's going to have all 22 fields. I can only show 4 on screen here, but some examples there. The success requirements: shut off fuel supply to heater in event of high pressure. It's a demand type, and we need to respond within 5 seconds. So what you're going to get in Profiler is a chart that looks like this with what you need to fill in and a place to fill it in. If the information is available from, say, the Silv determination already, it'll automatically be filled into this intended design. If you have a different number of fields or your own custom names for those fields, they can be customized, and you can change that within SafeGuard Profiler. The other section is the functional requirements, which is going to be on a per tag basis. So this column is automatically generated by Profiler with every element within your SIF, and there's about a dozen fields by default in there, such as what's your instrument type, set point, the failure state, and what reset action. Again, there'd be more of those if there was a little more space, and they show in SafeGuard Profiler. So we're going to fill that out, and the fields are available. If that information is available in your failure rate database, it is going to be automatically filled in. So we try to minimize the amount of rework you have to do by linking everything together from start to finish. So at this point, we're done our design stage. We've built the safety requirement specification. We've designed the SIF to the SIL2 reliability that we need to have. So through this, what has SafeGuard Profiler done for you? It calculated the reliability and PFDs for you without the need for using shortcuts or simplifications, because it's got a built-in failure rate database. It determined the voting configuration, saving you hundreds, if not thousands, of iterations of the voting formula. It built a reliability block diagram, so visualization of what the SIF is going to look like, and helped you determine the proof test interval you needed in order to make your current SIL rating, the SIL rating of the SIF, meet your required SIL rating coming out of the SIL determination. Also helped you perform failure mode analysis. So each of these elements, what can fail within it, and how do you deal with that failure? How often do you need to test? Finally, there's the SRS. SafeGuard Profiler has helped you with the intended design and functional requirements of the safety requirement specification, and helped you fill that out by providing the fields you needed and giving you as much information as possible already loaded into those fields. So that is SafeGuard Profiler in the SIL verification version. At this point, if you have any questions, once again, enter them in the chat or email them to me. I'm going to be jumping over to the tool in about a minute here, and we're going to be looking at some of the questions from earlier, along with I'm going to walk you through everything we just did in the PowerPoint we're going to do within the tool. And so what you're seeing on screen is actually the LOPA stage. So what we've done at this point is we've loaded the Hazop data in. I mentioned that I would show how you actually load that data in. So what I'm going to do is I'm going to go to a different project that I've prepared for exactly that case. And I'm just going to bring up Excel to show you what sort of data we're loading in. So what we're looking at is a Excel file with a whole bunch of Hazop data. This actually came out of PHA Pro is the tool. So it's you can create a spreadsheet that basically includes the information you want in the LOPA in any format. The column headings do not matter, nor do their order. And I'll show you why in a moment. But that's essentially, this is going to be the data that we're going to be loading into SafeGuard Profiler in a moment here. So this project has no Hazop information brought into it. So what we're going to do is just import that file. So I'm going to click Browse, grab the same file I had. And the next thing I'm going to do is load the column names. So that's going to, those columns that I had within the spreadsheet are going to be listed on the left here. Next thing I need to do is actually map those to what field they're going to be within the LOPA. So obviously node is going to go to node. If I have bowtie center, you may not. That's okay. You can put that in at this point. Likelihoods, we're going to be putting that in, etc. And then we're just going to accept that those columns are going to be displayed. The other thing we could do, we don't need to do this every time. We can take our settings from another project. In this case, I have a template, and it's going to automatically map all of those fields to the appropriate fields based on that template I created earlier. So once I click import, it's just going to take a moment here to actually load the data in. Now we're looking at the exact same data we had in Excel. And what we're going to have to do is, there is a bit of manual work here to group together the same consequences. So I'm going to right select on the consequences, and I'm going to find all my consequences that were the same. So in this case, I'm looking at a safety. So I'm just going to select those, and there's going to be a total of 5 of them that I know, and it does list that at the top right there. And then I'm just going to create loop, and it's going to be a LOPA type. And automatically now, that information has been generated within this scenario, and I can see it within the Silv determination. I can get started. I can give some PFDs to those safeguards. So once I've done that, there's a bit of time there, so I'm just going to jump to one where all of those have been grouped together. This is the same information I had earlier. You can view the Hazop. It's just all been put into scenarios. And I can go to Silv determination. This is what our data is going to look like. Causes listed on the left, consequences here on the right with all of our safeguards listed throughout it. If you need more information, everything's up here, including the numbering of the safeguards, more information about our cause, initiating, and event frequencies. If you want to get into the numbers, those are always available above. If you just need the visualization, which is typically what the LOPA participants are going to be doing, you can look down here. The first thing we're going to do is combine the alarms together. I mentioned that earlier. So I've moved from having 5 separate alarms to just one single alarm that's going to cover all of them, the high pressure alarm with operator action. It hasn't affected our LOPA graph, which is okay, but we've much simplified the bow tie. So this is a nice, clean looking bow tie. This is what you want out of a LOPA. That means you don't have excess instrumentation. The next thing to do is going to be to apply this SIL2 with that PFD to the SIF, which is number 3 in this one. You can see right now it's got no reliability, so it's thin. But once we apply that, that exact reliability, this is what our bow tie is going to look like. This is our SIF now, nice and thick. And our LOPA graph has exceeded the tolerable frequency, so we're good. You can see on the right, all scenarios are in a safe state. What you can do within the Expert package is actually link SIFs right back to the LOPA. So I've created this safety instrumented function, and I can just jump right over to the design of it from the layer of protection analysis. Ahead of time here, I've put in just some manual PFDs in order for it to show up there in the LOPA. I'm going to unclick those for both the sensor and the logic solver. Again, our logic solver, I'm going to get that value from the vendor, but the sensor and final element PFDs, I'm going to need to actually build using that reliability. First thing I'm going to do is add an element to our sensor. So at this point, I can choose my voting up there. I'm going to be typing in my sensor information, anything, a description, all of my failure rate info that I may have. I can fill all of that in. But I also mentioned we're going to want the failure rate data. So I'm just going to click failure data, and built into the tool is the ARADA 1997, 2002, and 2009 databases. So I can look for the information about failure rates there. As well, you can load in your custom failure rate database, which is going to be a comma separated value. Basically, it's going to be Excel. So we can look at some data that's been put in there. For example, for some real life information there. The sensor here that I'm going to grab, that's all the information that was in my PowerPoint. So I generate that ahead of time. It automatically puts the information in, including the tag, and it's going to calculate your probability of failure on demand. The final element, what we're going to end up with is a voting within voting, because a final element won't typically be just a single system. It'll be an actuator and a valve along with some other equipment. So what we're going to do is we're actually going to add sub-blocks, and this is going to be our valve configuration. And that's going to be a 2 out of 2. So I'm going to have a valve and an actuator, both of which have to work in order to create or to bring the system to a safe state. So now I'm going to add both of those elements in there and go back to my failure rate database and grab the actuator and the valve. Okay, our valve, and that's going to enter in all the information we need there. If I wanted to update some of these values, I certainly could. At this point, there's nothing keeping me from doing that. Won't let me put in a value that's non-existent. And what we get at the end is our probability of failure on demand, which is going to be that same value I calculated back in the PowerPoint. So we're at a still A at this point. I said that's not enough. So I need to go a little further. And the first thing I said I'd do is I'd look at voting. And so, for example, here, if we want the sensor, we want to go to 2 out of 3 voting on the sensor. This isn't going to have a huge impact on the PFD, but we're going to. But I'm going to show you how to do it. You can just copy the sensors and actually, just by right-clicking, paste them in here. And now I've completed my 2 out of 3 voting. Just give these different tags, maybe, so we have more information. And it slightly affected our PFD. You can also you can copy entire blocks. So I had 1 out of 2 voting on the final element here, and I just copied the whole block. And now if I paste that in, it's going to fill in all the information I need. Again, I'm going to want A's and B's. And overall, we've come to our PFD, again, the still one that I calculated back in the PowerPoint. This is at the point where we moved into the optimization. We haven't quite met it yet. So our target here, our current SIL, is only a SIL 1. So let's go into the optimization mode, where now we can select what we want to pivot the equation on, essentially. So I wanted to do the test interval. So I'm going to select this value, and I want to change the test interval for all of the equipment within this SIF. So I'm just going to select this entire column. If I wanted to, I could pivot this equation on just the failure rate of a single of the sensor, say, and I would just select those 3. But in this case, it makes no sense to do the test interval of just a single element. Okay, so next thing I'm going to do here is, here's my Silv graph. I'm just going to drag that over to the SIL range that I need, and it's automatically calculated. I used to have a test interval of 60. It's now calculated I need 33. And as I drag that along, it'll change it depending on what I need in terms of reliability. You can even figure out what is the maximum theoretical SIL I could get with this system. So if I drag it all the way to the right, it'll automatically plunk it in and say my test interval at basically testing every single day, I could theoretically get a high SIL 3. But if I wanted to, I could make this system SIL 3 compatible. If I was testing it around yearly, I could get a low SIL 3. Otherwise, I'd have to come up with different equipment. So again, you can change that as much as you want to see the impact. And as I mentioned earlier, you can actually change this equation based on any value. I'm going to deselect them here. If I just want to look at what type of failure rates for the sensors, so maybe I want to instead find a different sensor at this current rating. What if I wanted to bring that up further? Well, I need a really low failure rate in order to just get a SIL 2. So once again, you can pivot that equation based on any of these values as long as they're within the same column. The laws of mathematics say that it has to be in the same column. So what's going to happen at this point is our SIF is complete, or at least the validation there for determining what your probability of failure on demand would be. And if we go back to the LOPA, we can actually see in our bow tie diagram in the solution case, it is linked back the SIF. There's our reliability we calculated, so it's slightly different than the original. They're linked together and will always exist together as separate or as a combined database. That's if you have the expert package. I'm just going to jump back to that. And I talked about the SRS as well. Let's just jump over to the safety requirement specification. Here's our 22 fields, all available. Whatever information can be brought in is going to be. So there's our references, there's the name. If I had done a little bit more engineering there and the validation parts of these other ones would be filled in. But just generally, I'm going to be filling in our spurious trip rate, the restart process, all these values that I mentioned earlier, mode type here. I'm just going to be typing those in, and that's going to be saved. Also included in the SRS is our reliability block diagram. So let me just grab a bigger version of that. What we're looking at there, here's our 2 out of 3 voting on the sensor, 1 out of 2, 2 out of 2 for the valve configuration. It's all there within the reliability block diagram. At this point, you've completed your both your SIL determination and your SIL validation, at least once you've filled out this safety requirement specification, and you're done. You can print out your reports and you can go on to the next quadrant and actually design or build your SIF within your facility. Are there any more questions with regards to this? I see there's a couple. One of them is about online training, and yes, we do provide online training for use of this tool. We do WebEx sessions just like this one fairly regularly, and that can definitely be arranged. The one is, what is the implication if validation's not done? You can't have a SIF without validation, so you don't need to do validation on every single loop within your system, just the ones you want to meet the 61511 standard. And how do you know the SIF configuration from a PNID? You don't. A PNID doesn't necessarily show that information. It may show some voting. I've seen some PNIDs that do, but there's no guarantee of that. The PNID doesn't show SIFs. That's where you go to the safety requirement specifications for your facility. Further questions about online training? There, both SIL determination and SIL verification are available. We have training on those, how to do it, and that's independent of SafeGuard Profiler. However, that is in the office. We don't have online training. We only provide the online training for use of the tool. But if you want to do SIL determination or SIL validation courses, you can actually even go on to get your TUV Functional Safety Engineering certification through ACM Facility Safety. We provide that training. If you have any more questions at this point, please feel free to email them to me. I'll be happy to answer them or forward them to someone who can answer them. Please get back to us if you have any questions, comments, or if you'd like to know more about SafeGuard Profiler or our other tool, SafeGuard Sentinel. Thank you.